Is that okay? Mr.
Yes, sir.
Bagal?
Presentation.
Hi, you are able to see in my screen, right?
Yes, we can,
Yes,
but
sir.
go in the presentation mode, please.
Okay, yeah. So I will start now.
Yes.
Okay. Uh, very good morning, Professor Gandhi, Mr. Bagli, IGS President, Professor Shiv Kumar Babu, President-elect Professor Madhya, Conference Chair, Professor Satyanarayan Reddy, all other senior professors online, and all the distinguished delegates who are attending this particular session. Uh, at the outset, let me thank the organizers, particularly the Indian Geotechnical Society and the conference chair, Professor Reddy, for extending to me this particular invitation to deliver this keynote lecture in this conference. I'm going to speak primarily on some aspects of seismic soil structure interaction of lifeline structures. Now, when we talk about lifeline structures, these are somewhat different from the conventional structures like buildings or dams. I'm basically talking about tunnels in the metropolitan areas which are used for the mass rapid transit system, the various water conductor systems in the hydropower projects, roadway and railway tunnels in hill areas. We have in India, for example, Jammu, Udhampur, Srinagar railway line. Similarly, the presently under construction Rishikesh Karnaprayag railway line, the proposed Bilaspur Manali Leh railway line project, and you are all aware recently the Prime Minister inaugurated the Atal tunnel, which is basically a transportation tunnel or a highway tunnel. Similarly, we have the Jojila Pass tunnel. But then apart from these tunnels for different purposes, we also have the gas and water transportation pipelines. And similarly, the bridges which cross the valleys in hilly regions. Now, these are the structures actually which are very long in comparison to their cross-sectional dimensions. You have got the pipelines which run over a length of a few hundred kilometers. You have metro underground systems which run over a length of few kilometers. And you have the railway line projects in hill areas which run to a length of about a few hundred kilometers. Underground structures were earlier considered as less vulnerable to earthquakes as compared to above ground structures like tall buildings, dams, which are built on the ground surface. However, the 1995 Kobe earthquake, or let us say the 1999 Chaichai earthquake in Taiwan, these have clearly demonstrated that several underground structures, they can suffer severe damages depending upon the various parameters at a site. And therefore, the underground structures cannot be treated as completely exempt to the effects of ground shaking. In India, there is a growing need at present to enlarge the infrastructure, especially in the hill areas, or we have got mass rapid transit systems, their networks in the metropolitan cities, all-weather connectivity in hill areas, particularly the northern and the northeastern states, and also connectivity in strategically very important areas from the defense point of view. So because of these, there is a renewed interest for studying the vulnerability of the lifeline structures to seismic loading. A large earthquake, in fact, causes direct damages in the form of excessive settlements, tilting, or severe cracking of structures, and sometimes even the collapse of structures. Whereas there are also the indirect damages in the form of fires, explosions, which result into potential loss of human lives and damage to the infrastructures, damage to the adjacent infrastructures. All this causes severe economic losses, especially in view of the time that is required to restore the functionality of various infrastructures. It is therefore essential to reduce the possible associated damages and also the consequent effects of these damages. Most of the tunnels, so there are some important observations on basis of the earlier failures which have taken place in case of such lifeline structures. Most of the damaged tunnels were located in the vicinity of the causative faults, causative geological faults. The ground motion, which is close to the active geological fault, may be characterized by strong, coherent, narrowband, long-period pulses. And this ground motion is severely affected by the rupture mechanism along the fault plane, the direction of rupture propagation in relation to the particular site in question or a project in question. And there can be also permanent ground displacements which result from the slip along the major geological fault planes. On basis of the study of damage to about 71 tunnels excavated in rocks due to earthquake shaking, and their comparison of the behavior with the estimated values of peak ground acceleration and peak ground velocity suggests that collapse of the tunnels due to ground shaking occurs only under extreme conditions. It was found that damage did not occur so long as the PGA values are less than about 0.2 G or the PGV values are less than about 0.2 meter per second. Minor to moderate damages were observed when the PGA values approached about 0.5 G, whereas moderate to heavy damage was experienced when the PGA values exceeded a value of 0.5 G. And the tunnel collapse occurred only when it was associated with the movement of the intersecting geological fault. The strong ground shaking actually can cause also the liquefaction in saturated sands, and with consequences like sinking of the structures or shifting of the ground surrounding the tunnels, which leads to collapse of multiple underground structures. And the famous case is that of the collapse of a subway station during the 1995 Kobe earthquake in Japan. This liquefaction is also responsible for causing the landslides, consequently the damage to highway facilities. Landslides also generate secondary impacts. And there occurs a rupture of water and gas supply pipelines, and more importantly, the electrical transmission lines, which cause actually dramatic explosions and fires. This was what exactly happened during the 1994 Northridge earthquake in USA, when the ruptures of the gas pipelines occurred. The net outcome of this is that seismic analysis of underground structures is a complex task, as it involves interaction of several disciplines, including structural geology, the seismotectonics, engineering seismology, soil and rock dynamics, and also structural dynamics. And this area has remained by far somewhat neglected, primarily because of the conventional notion that the underground structures are not sensitive to earthquakes. As a consequence, design engineers often omit the evaluation of structural performance of tunnels and such lifeline structures under seismic conditions at the design stage. Let me just bring out some of the design considerations which should be followed while carrying out initial designs. The first one is that seismic response of tunnels and underground structures is considerably different from that of above ground facilities, because the overall mass of the structure is usually very small as compared to the mass of the surrounding soil or rock mass. The overall confinement of the underground structure by the surrounding soil or rock mass provides high level of radiation damping, and as a result, seismic response of underground structures is basically controlled by the induced ground deformations rather than the inertial characteristics of the structure itself. In case of underground projects, particularly in the urban areas, design and construction is more demanding because of the interaction between the underground project and the overlying pre-existing structures through their foundations. And these are the issues where the people go to the court of law to seek the compensation in case the above ground structure is damaged or affected by the underground activity. The interaction of these underground, lifeline structures is basically a function of the depth of overburden or the thickness of the overburden above the bedrock, and the nature of topography, particularly in hill areas. The topography is very uneven. This results into what we call as a seismic amplification, and this seismic amplification was the cause of damage to bridges during the 1995 Kobe earthquake. And it was also the cause for damage to the underground tunnels and buried gas pipelines during the 1999 Chai earthquake in Taiwan. So therefore, the selection of realistic ground motion is very important from the seismic analysis and design point of view of these lifeline structures. The time history of earthquake has to match the expected earthquake in that particular zone or at the particular project site in question, and hence there is a need for what we call as the response spectra compatible time history. I'm going to take very briefly the case of Delhi Metro underground tunnels, particularly constructed in the early phase 1. And this is a typical cross-section of the DMRC tunnel in Delhi. Delhi lies, this is the geological map of Delhi city. You have got the Yamuna river running or flowing in the north-south direction. And you have got basically either the younger alluvial deposits or the sandy silt deposits below the ground surface in Delhi city. And in some portions in the north-south direction, you have got also the quartzitic ridges. The tunnel diameter is about 6.26 meters, and the depth of overburden above the crown of the tunnel is about 16 or 17 meters. The tunnels are provided with precast RC liners, and you know very well that Delhi lies in a seismic zone 4 as per the seismic map. The modulus of the soil mass varies from ground surface to with a value of about 7.5 megapascals to about 50 megapascals at a depth of about 60 to 70 meters below the ground surface. We tried to study the behavior or response of these tunnels subjected to Chamoli earthquake. I will explain as to why we consider Chamoli earthquake only. This plot shows the horizontal acceleration time history with a PGA value of about 3.667 meter per second square. That's the vertical acceleration time history with the PGA value of 1.557 meter per second square. This plot shows the Fourier spectra of the Chamoli earthquake of 1999 with a predominant frequency of about 1.67 hertz corresponding to the horizontal component, and with a predominant frequency of about 11 hertz corresponding to the vertical component of the earthquake. So in order to develop the response spectra compatible time history, we tried to generate the target response spectra on basis of the IS code 1893. This was generated both for the maximum considered earthquake as well as the design basis earthquake for different values of damping ratios of Delhi silt corresponding to about 5%, 10%, and 15%. That's the typical response spectra for the maximum considered earthquake for zone 4 of Delhi for different values of damping, including 5%, 10%, and 15%. So I find that corresponding to the minimum value of damping, I've got a maximum PGA, which is of the order of about 0.6. This is the response spectra corresponding to the design basis earthquake, and I find that the magnitude of SA upon G is roughly half of that for the MCE. Then we have to select adequate time history. In fact, in Delhi, there is no record of a major earthquake. So the nearest earthquakes were 1991 Uttarakashi earthquake with a magnitude of 7.0 and a PGA value of 2.37 meter per second square. And the 1999 Chamoli earthquake with a magnitude of 6.8, but a PGA value which is much higher than the PGA value for Uttarakashi earthquake. This is 3.53 meter per second square. Now this Chamoli and Uttarakashi, these are the places which lie in zone 5 of the seismic map, whereas Delhi city lies in zone 4, and therefore there was a need to generate artificial time history for Delhi city. So taking a magnitude of acceleration from the target spectra and a phase from the input history, response spectra compatible time histories were generated using these three software packages, SPEC3 and WaveGen. These are the two packages which were developed in IIT Roorkee. And the third one is Seismomatch, which was developed by Hancock and his team in the year 2006. And the typical observation is that the trend of the artificial time history generated by Seismomatch software developed by Hancock is quite similar to the actual earthquake, except for a difference in the value of PGA. So this is a typical response spectra compatible time history obtained by the seismometer software corresponding to 5, 10, and 15% of damping ratio. So when I try to see the effect, I find that both for MCE as well as DBE, the PGA values go on increasing as the damping ratio goes on reducing. When I study the horizontal displacements of the soil tunnel system, I find that the seismometer software gives me a value of about 200 mm near the ground surface and very close to it at other points around the periphery of the tunnel, including the crown, the invert, and the springing points. And DBE also, the design basis earthquake, also gives me the same range of horizontal displacements. As far as the vertical displacements are concerned, all the three software packages or all the three response spectra compatible time series for MCE and DBE give values which are very close to each other at all the critical points, including the periphery of the tunnel and the ground surface.
Professor, only 5 minutes left.
Okay. So therefore, what are the most important thing that I have observed is that the presence of tunnels below the ground surface or excavation of tunnels modifies the response at the ground surface, and therefore the structures lying on the ground surface or constructed on the ground surface, they are significantly affected. We try to consider the three-dimensional analysis also, especially because you all know that these lifeline structures like highways or underground highway tunnels or railway tunnels underground or the gas supply pipelines, all these are the facilities which extend over length of kilometers. And you can have a significant change in the geology over length of few hundred kilometers. You may have many geological discontinuities which can come into play, and therefore it is essential to study the 3D response of these underground structures, particularly the longitudinal direction or the actual direction of tunnels. So this is the typical response spectra compatible time history corresponding to transverse component. That's the vertical component, and that's the response spectra for the longitudinal direction. So when we try to consider these response spectra in all the three directions, I find that maximum horizontal displacements are affected essentially by the transverse component of the earthquake, whereas maximum vertical displacements are affected both by the vertical component as well as the longitudinal component of the time history, and the longitudinal displacements along the axis of the tunnels, they are affected both by, again, longitudinal component as well as by the vertical component, especially at the ground surface. Now, so what I find is that 3D analysis actually gives a higher value of horizontal, vertical, and longitudinal displacements in the soil tunnel system corresponding to all the three components. And 3D analysis in general gives a much subdued response as compared to any 2D analysis. Then we try to consider a significant parameter in the form of liquefaction, because you are involved with a geological strata which runs over a length of few hundred kilometers. It is essential to consider the aspect of liquefaction. Earlier studies have shown that safety of underground lifeline structure improves against liquefaction damage with increase in depth of overburden. Liquefaction leads to mobilization of high uplift in the soil tunnel system. Liquefaction also leads to increase of forces in the tunnels, and the acceleration response at different depths was found to attenuate significantly due to occurrence of liquefaction. We try to carry out numerical modeling of this liquefaction phenomena, particularly for these Delhi metro tunnels, and using what we call as the UVC model for the constitutive relationships. In terms of pore pressure ratio, which is basically in terms of the effective mean stresses, and the state variable R sub U, which is in terms of the effective vertical stresses. When I try to compare the pore pressure ratios which are developed or mobilized I find that they are less than 1 corresponding to the horizontal and the vertical components. But when I go to the response corresponding to the longitudinal component, I find that both the pore pressure ratio and the state variable R sub u, they exceed the value of unity, indicating that longitudinal component of earthquake can cause liquefaction and therefore damage to the underground structures. When I study the effect of the depth of the water table, of course, as the water table rises, there is a tendency of or possibility of liquefaction taking place. And particularly in case of Delhi metro tunnels, when the water table rises from a depth of about 10 meters towards the ground surface, then there is a possibility of liquefaction. Existing level of water table is about 17 meters below the ground surface. When I study the effect of PGA values, I find that up to 4 meters per second square, the tunnels are safe. But if the PGA value goes beyond 4.0, there is a possibility of the occurrence of liquefaction. So my final recommendations as far as analysis and design of lifeline structures is concerned, the first one is that design engineers should seriously undertake at the design stage only evaluation of structures in cluster areas and in metropolitan cities where the underground activity is going on, particularly against earthquake. Secondly, the road and rail transportation tunnels in hill areas and other infrastructures like electrical transmission lines, etc., should not be aligned in the vicinity of the geological causative faults. This aspect can be taken care of right at the planning stage only. The third recommendation is that lifeline facilities with lesser depth of overburden are more prone to damage. As a consequence, construction of tunnels modifies the response at the ground surface, and hence in urban areas, especially in metropolitan cities, response of the above ground structures due to construction of underground projects needs to be thoroughly investigated. Otherwise, it gives rise to problems of litigation. The fourth recommendation is the effect of local site conditions, particularly the thickness of the soil layer above the bedrock and the uneven topography. This must be taken into account during the design of structures like bridge abutments in hill areas and the alignment of the transmission line towers, alignment of highways, or alignment of railway tunnels in hill areas. It is also essential to generate the response spectra compatible time histories specific to particular zone or a particular site in question. In case of lifeline structures,
your time is up.
Just 1 minute only. It is essential to carry out to understand the 3D response, particularly because the longitudinal component of the earthquake can cause either damage to the below ground structure, or it can bring about liquefaction and consequent damage to the lifeline structure. The liquefaction in hill areas can also give rise to landslides and therefore damage the highway facilities. It generates secondary impacts and may cause the rupture of water or gas supply pipelines and uprooting of the electrical transmission lines. Thank you so much, Mr. Chair and Co-Chair. Thank you for giving me enough time to finish my presentation. Thank you so much.
Thank you, Professor. You didn't exceed much.
Yeah.
Okay. Professor Gandhi, please.
Yes. Thank you, Professor Viladkar, for the very interesting talk. You have covered the stability of the underground tunnels, effect of liquefaction, and given a message that sometimes the horizontal acceleration could be more serious to the underground utilities as well as for the hill slopes.
Particularly in the direction. Yeah.
Right. Now, while I was reading your biodata, there was some problem with the network connection. Am I audible now?
Yes, yes.